Hello guys, and welcome to a video on first order differential equations. So, what is a differential equation to start off with? So, a differential equation is anything of the form dy of dx is equal to f of x and like a variable of x and y. Where this isn't a partial derivative if you get confused by that. A partial derivative is where f of the function of x and y is equal to z. But we're only considering we're only considering x variables and y variables for now. So we're going to start off with separating the variables. Separating the variables is relatively easy. It's not too bad once you get into the swing of things. So I'll show you just two examples, and then the rest of it you'll figure out. So the first example we're going to do here is a differential equation. So what we've got here is we have got find the general solution of 1 plus x squared dy by dx equals x tan y. That is our differential equation. This is actually fairly easy to do. So what you do here for separating the variables, as you have a dy and as you have a dx, what you do is you collect all of your x terms on one side, and then collecting your y variables on the other side. And that's why it's called separating the variables. You have two different variables. You take one variable, all one variables and constants on one side, and then the other variables or constants on the other side. So let's just do this quickly. So let's go through this example. So 1 plus x squared dy by dx equals x tan y. So what we're going to do here, what we're going to do is we are going to divide by 1 plus x squared and divide tan y and then times dx on this side. So this is what we're going to do. So dy by dx is equal to x tan y divided by 1 plus x squared. So what we're going to do now, since we've collected 1 plus x squared on this side now, what we're going to do is we are going to divide tan y to bring it onto this side, so it becomes 1 over tan y, which is going to become cot y. And now we're going to times dx onto this side. So you have all your x terms on one side and all your y terms this side. Just let me show you for 1 second. So 1 over tan y dy is equal to x 1 plus x squared dx. Now do you see now that I've collected all my y variables on one side and all my x variables on the other side? Now do you see that? Okay, good. So now what we're going to do, we're going to integrate both sides with whatever respect we're doing to. So on this side we're integrating with respect to x, and on this side we're going to be integrating with respect to y. So what we're going to do is the integration of cot y with respect to dy, integrating x over 1 plus x squared, which I think is looks like an arctan, but oh no, sorry, it's a first guess, second guess. Dx. So what we're going to have on this side is, what was it? Ln sine y. Ln sine y is equal to first guess, second guess. So when you differentiate x1 plus x squared, you get 2x, which is very close. So it's going to be half x. So that's going to be half ln 1 plus x squared plus, we're going to add ln c. Ln c is just our constant here. That's all it is for now. Okay, so what we're going to do now, we are going to times these together. So what we're going to do is, oh sorry, I forgot to mention as well, we're going to take this power up here. So what we're going to get is ln sine y equal to ln, we're still going to continue calling this c. So the power of logs is that if you have ln a constant plus ln a constant, it just becomes ln, and you times those two constants together. So what we're going to do, this is now ln 1 plus x to the power, 1 plus x squared all to the power of a half, square root of 1 plus x squared. You should recognise that, definitely. So now, what we're going to do is, we're going to eliminate lns on both sides, so we end up with sine y is equal to is equal to c 1 plus x squared. And we're just going to leave it like that. This is our general solution, because otherwise it will just be too complicated. You know, y equals arc sine c. It's just hideous, and there's no point doing so. This is the general solution. Usually most exam questions, or rather all exam questions that will have differential equations, will say find the general solution to this. And then you'll have to answer a part B question where it says, with these boundaries where y equals 0, x equals 0, or dy by dx equals a half, or something like that. And then you've got to find your constants. You find your constants, and then you find the particular solution. Because with the general solution, you keep your constants in. In a particular solution, you don't, and therefore you keep your constants in when you find the general solution of this differential equation. So we're going to just move on to another one. That's what we're going to do. So dy by dx is equal to minus y over x. So what we're going to do, we're pretty much going to be doing pretty much exactly the same thing as last time. We're going to be separating the variables. So you take all your x's, so you take all your x variables on one side and all your y's on the other. Preferably take the y, let me start again. So what we're going to do is we're going to take our x variables on one side and take our y variables on the other. So if we divide y and times by dx, we are going to end up with dy over y equals, so times in dx, minus dx over x. You can put, it doesn't matter what you put, but you can put 1 over y dy or 1 over x by dx, but it doesn't really matter. It means exactly the same thing. So what we're going to do, we're going to integrate both sides. So we're going to end up with dy over y, it's essentially 1 over y with respect to dy, but we're just going to put dy for simplicity, equals the minus, we're factoring that minus out because we don't need it, dx over x. Or 1 over x with respect to dx, doesn't matter. So when we integrate 1 over y, we're going to end up with ln y. You can put the modulus signs. It just means it's greater than 1. It will always be greater than 0. It just deals with a whole load of errors, because as soon as you set ln 0 to, when you put in ln 0, it's going to tend to infinity. That's what's going to happen. That's why it comes up with an error all the time. So let me just get on with this. So when you integrate 1 over y, you're going to get ln y. When you integrate 1 over x, you're going to get ln x, with the mod signs, of course. And we're going to add a constant as well. So we're going to call this ln a. Preferably, I prefer to call it a for because this is an arbitrary constant. An arbitrary constant means the constant value can be pretty much anything. It doesn't really matter because this is a general solution. So what we're going to do, we're going to take x on both sides. Sorry, we'll rearrange it for x to go on that side. Sorry, you'll see what I do. So ln y plus ln x is equal to, we're going to actually call it ln c, but we're going to call it, we're going to keep ln c for now. When you obviously laws of logarithms, so it's going to be ln xy equals ln c. And now what we're going to do, we're just going to get rid of the ln signs, or basically everything, if you get what I mean. So we're going to call this a for now. And now y is equal to plus or minus a over x. The reason for the plus or minus, I was meant to put modulus signs there, but it doesn't particularly matter, if I'm being honest. As long as you recognize that this is a plus or minus, then it should be fine. Now, the reason it's called a general solution, if I draw the graph of plus or minus a at x, where a is an arbitrary constant, so a could be any value between anything greater than 0, basically, and not including 0. So if I can call that y-axis and x-axis. So this is what it's called a family of solutions. A family of solutions essentially means when you have an arbitrary constant greater than 0, it can be essentially anything. So it can be like that, or that, or that. So it's like that. So you can have many different solutions. Just remember that each correspond. It doesn't really matter. But you're not going to get asked to draw a family of solutions. The only reason I'm showing this is why it's called a general solution, because when you have an arbitrary constant, it can be any one of these. It can be 3 over x, 5 over x, minus 7 over x, minus 9 over x. Doesn't matter. It'll be an arbitrary constant for a reason. So now we've essentially finished separating the variables. It's not hard. It really isn't. So what I'm going to do, I'm going to set you some exercises and see how you do. Okay, so here are just 3 simple separating the variables exercises. So for each of these questions, find the general solution of the differential equation. So we have dy by dx equals 2y over x, dy by dx is equal to cos x, and dy by dx is equal to y cot x, where cot x is 1 over tan, or cos over sine, doesn't really matter. And it's between the range of 0, where x is between the range of 0 and pi. That is the range of cot x, essentially. Okay, so what we're going to be doing now is the integrating factor. Integrating factor is much easier than you think. It essentially comes from implicit differentiation. So I'll show you that in one moment. Okay, so separating the variables is not the only method on finding the general or particular solutions of the first order differential equations. There are in fact 3. Separating the variables, an integrating factor, and then there's something else as well, which I've completely forgotten on. But integrating factors is more or less the same method. The two of the methods are essentially the same method, so it doesn't really matter. Find the general solution of. You're probably So you're probably thinking, what the hell? What the heck? How are you going to do this? You can't use. There's no way that you can use separating the variables. That's why we have integrating factors for. Okay, so what I'm just going to teach you for a second. This is a reminder on implicit differentiation. So, if you notice, what is the derivative of y? The derivative of d by dx of y is equal to dy by dx. Yes? That is the first derivative of y. D by dx, x cubed, is equal to 3x squared. Okay. What do I do with these? For the smart people out there, you should have recognized that the derivative of x cubed is right here, 3x squared. So x cubed and 3x squared. Also considering that the derivative of y is equal to dy by dx. So what's going on here? Have we got... is this a product rule? Is this a implicit product? Well, I am definitely correct on that one. So let me just show you for a second. So if you differentiate x cubed y, for example, what you're going to get is x cubed. You're going to keep x cubed as it is, so you set u to x cubed and v to y. So it's going to be u dv by dx, so x cubed dy by dx, plus v du by dx, rather than that, equals sine x. So what we can do, we can actually, since d dx, x cubed to the power, x cubed y, is a product of this, we can actually turn this, essentially this is the reverse products implicit rule, essentially. So you're reversing the product rule and turning it into this. So what we can say is that d dx x cubed y is equal to sine x. That's what we can say, genuinely. So now if we have, because one, I've already explained, but for those of you that still don't get it, I think you need to go back to implicit differentiation and just look this over, because this isn't an easy concept to figure out unless you've already done, say, A-level maths or calculus 1 or 2 in the US, it doesn't matter. But x cubed y, the product of this is equal to x cubed dy by dx plus 3x squared y. So now what we do, we integrate both sides with respect to x. We don't need to put respect to x on this side because we already have the d dx. So what this does, that cancels and we're just left with x cubed y is equal to minus cos x plus c. That is what we're left with. Okay? So, what's next? Just divide by x cubed. So we have minus 1 x cubed cos x plus c over x cubed. And that is our general solution of the differential equation. Sorry. So let me just go over what had just happened. So what we have, we're trying to find the general solution of x cubed dy by dx plus 3x squared y equals sine x. So realizing that u and v, so u and v, you basically combine them together and create d dx x cubed y, where d dx just means the derivative of x cubed y. That's what it means, just the derivative. And then obviously this derivative creates this equation on the left hand side. And then now what we've done is that the derivative of x cubed y, if you integrate the derivative, it just gives the original uv function, and that's it. That's literally just how it is. And then you rearrange for y. It's not difficult at all. It really isn't. So now we're going to, this is the second method. So eventually reverse product implicit. Now what we're going to do, we're going to move on to a third method, and this one isn't particularly easy. This one is the integrating factor. This isn't an integrating factor. This is just identifying what u and v is, combine them together, and then whatnot. I've already explained it so many times, you probably fell up of it. So let's move on. Find the general solution of the differential equation of dy by dx minus 4y equals e to the x. Okay, so the problem is that we have no product anymore. There is no definitive way that we can find the differential equation. We can't, how the hell can we get y straight from just this, including this e to the x right here? It's actually easier than you think. So, you can solve a first order differential equation of the form dy by dx plus v plus p px y qx. So what we're going to do is this, you have to look carefully here. So the equation here, to find the integrating factor. So the integrating factor is always e to the power of minus 4x. Yes. Sorry, it's e to the power of minus 4 with respect to dx. Sorry, let me start again. So the integrating factor is whatever's on this side, and you times it, so it's e to the power of the integration of minus 4 with respect to x. This might seem like a really weird concept, but in time, it'll come. So, I'm just going to go through more examples so you just fully understand what's going on. So, e to the power of the integration of minus 4x. So what this is pretty much just e to the power of minus 4x. We don't put a plus c, we just don't, because there's absolutely no point in doing so. Okay, so what we've got, so this is now our integrating factor. So what we're going to do, we are going to times everything in this differential equation. So now we have e to the power of minus 4x dy times dy by dx minus 4 e to the minus 4xy equals e to the x times e to the minus 4x, which then becomes just e to the minus 3x. Okay? So, we now have our integrating factor here. So when you differentiate e to the minus 4x, you have minus 4 e to the 4x. And obviously your v product is y. So now we're going to have the differential of e to the minus 4x times y is equal to e to the minus 3x. Yeah? Okay. That is literally what we had done in the last example. That is what we've done. So all we've done is just added this integrating factor. And it's pretty simple. It's not too difficult whatsoever. So now you integrate both sides. That's respect to dx. The derivatives cancel. End up with e to the 4x times y is equal to minus a third e to the minus 3x plus c. That is what you end up with so far. Okay. So, what we're going to do, we are going to divide by e to the power of 4x. So when we do that, we end up with y is equal to a third minus a third e to the x plus c e to the 4x, because that's a reciprocal. Yeah, that's what we get. And that is our general solution. So let me just go through it one more time. So we're finding the general solution of dy by dx minus 4y equals e to the x. We need an integrating factor. So the integrating factor is whatever is with the y. So it's minus 4. And that is integrated by e to the power of the integration of whatever is in the y term. Yeah? Okay. And then obviously we just do exactly with the same thing. You find your product, you find your implicit, and then you integrate both sides, they cancel, and then just rearrange for y. And now you found your general solution. Yeah? Excellent. So we're just going to move on to another example. Okay. So what we are going to do here is we are going to divide. Okay, so let's just start where we think. Let's just start from where we can think we can go. So we can't immediately just do the integration factor. The only way that you can actually do the integrating factor is if a dy by dx is on its own. So what we need to do here is that we need to divide by cos x all the way through. Okay? So divide by cos x. So we end up with dy by dx plus sine over cos. So 2 sine over cos is equal to 2 tan. That's just the symbols I give it. Dy by dx plus 2y tan x is equal to cos to the power of 3x. Okay? So, our integrating factor is now going to be 2 tan x. So, I'm just going to put IF. So, integrating factor is e to the power of the integration of, we're going to factor the 2 out, tan x dx. That's what we're going to be doing. Okay. So when we integrate tan x, we are going to end up with 2 ln sec x. Oh, sorry. What about that? Is that correct? Pretty sure. Yeah. So it's going to be 2 ln sec x, which then using the power law from logs, e to the power of ln sec squared x, and because e to the power of ln cancels, and there's no 2 in front of it, that cancels. And now we're just left with sec squared x. So sec x squared is what we're going to be. Sec x squared is what we're going to be using when we're going to times everything together. So when we times sec squared x by everything, we get sec squared x times dy by dx plus 2y tan x sec squared x equals cos x sec squared x. Okay? That is what we're going to get. So you times everything by your integrating factor once you've manipulated it into an e to the ln sec squared x. Something like that. And then it just leaves with sec squared x. Okay? There's one thing you might have noticed here. Sec squared x is actually 1 over cos squared. Those cancel. Did you know that? Because I would write it somewhere, but essentially because this is times 1 over cos squared x. The 3 cancels and you're left with cos x, and that's literally it. It's very clever. It's really clever how all this stuff works. It really is. So essentially now, when you differentiate sec squared x, you will end up with 2 tan x sec squared x still. So now what we're going to be doing is setting your derivative up. So your derivatives are going to be y sec squared x. So sec x is your u, y is always going to be your v. It's equal to cos x. Integrate both sides. They cancel. That turns into sine x plus c. That turns into y sec squared x. So now y is equal to sine x over 1 over cos squared x plus c. Sorry. I'm going to just name this a different. I'm going to call this k. So k cos squared x. That's what we're going to be doing. Cos squared. 1 over cos squared is equal to sec squared. Just a reminder. And then just rearrange so you end up with sine x cos squared x plus k cos squared x. And if you really want to, you can factorize this. So cos squared x is equal to sine x plus k. Yeah? And that's literally it. That is the general solution. So y equals, and that is the general solution. I'm going to show you very quickly how you work out the particular solutions to this. So you'll be given in the original equation when when y equals 2, x equals 0. So what do you actually do with this? First off, when you're being asked, find the particular solution, you have to find the general solution first. So you have to get all the way down to this point here. So when y equals 2, x equals 0. So when we do this, 2 is equal to cos squared x is, cos 0 is 1. So it's going to be 1, 0 plus k. So k is going to be 2. That's pretty simple. And your particular solution, oh sorry, I don't know if you can see. So your particular solution, this is essentially the solution that determines, your boundaries. This is a particular boundary. So your particular solution is equal to y cos squared x sine x plus 2. That is the required particular solution. That is what you usually get. This is pretty much a box standard differential question, essentially. So I'm just going to give you some exercises and then we'll literally finish up on first order differential equations. The next time I'll come back to different first order is when we do reproducible equations, where you use a transformation to turn into differential equations. Sorry, use a transformation to work out the solution and then you essentially convert it back. Okay?